Well, thank you to you two for being here. You're officially my studio audience. You have any questions about anything from last time? Or anything? Okay. Yeah. After this class, I'm going to head to Thorntown, Indiana to view the eclipse. Let's see. So today it's an exciting lecture, so I'm recording it so everybody can hear it. I'm going to talk about the fundamental theorem of calculus. It's a beautiful, fairly natural thing to do, even in freshman calculus. But now that we understand real analysis a little better, I want to talk about some of the interesting things that fall out of it and different ways of thinking about it. So an important thing from last time is that if two functions are Riemann integrable on AB and they satisfy an inequality less than f less than or equal to g on AB, then of course the integrals are also less than or equal to. You can, if you draw a picture, that just means the area under the curve of the graph of f is less than or equal to the area under the graph of the g. But if I was going to prove that using definitions and basic tools, it would be that if I took a partition and took why don't I take an upper sum of a partition for the f integral, that would be equal to the sum of the soups of the f's on the intervals times the I'll call that m super n f. And of course, f being less than or equal to g, that's less than or equal to the same thing for the g integral, for that partition. So m sub g on the nth subinterval. And that's less than or equal to, well, it's not less than or equal to, let's see. Let me change this to L, the lower sum, and I'll change. That would make this a nth minimum kind of thing, and then this would be the same thing for the G's. And that would be less than or equal to the upper sum of G for that partition. And we can choose a sequence of partitions so that those lower sums of f head up to the integral value, and then we can choose. And if we take the union of those partitions, we can do one for G too that goes down to the integral of f. So we take P1 and P2s, and then we take their union and squeeze it even more. Anyway, it's not a hard thing to show from the basic facts we've been doing. So I guess I'll say it in words. Take P1 making L PF close to the value of the integral. That would be the lower f equals close to this value of the integral. And then take P2 making U, this is P1, this is P2, G close to the value of that integral. And then when you look at this inequality for the union, those two things get squeezed even closer together. So we squeeze LF and LG, etc., all those numbers, using the union of those two in that inequality above. P equals P1 union P2. So it's a natural thing. So let's see. Here's the theorem I'm going to prove first, which I think is the most natural, easy one to do. Theorem. If f is continuous on AB, then if I define capital F of x to be the integral from a to x of f of t dt, that t is just a dummy variable here, then this thing is differentiable. Then f is differentiable on AB, and its derivative is little f. That's the basic fundamental theorem of calculus for all x. Okay, and it's going to be easy and natural, and very much like you would see in freshman calculus. So my favorite proof does this. Let's see. We know that continuous functions are Riemann integrable. So we know continuous functions are Riemann integrable. And we also know that if f is continuous, then so is its absolute value. If f is continuous on AB, then so is its absolute value. That was exercises back when we were learning basic facts. So is the absolute value of f. Okay, and so here's an important lemma. The integral, or that's the absolute value of the integral from a to b of f dt or dx or whatever, let's take dx, is less than or equal to the absolute value, what am I saying? No, it's less than or equal to the integral of the absolute value, dx. That turns out to be an easy thing. So here's why. We would have minus f less than or equal to f less than or equal to modulus of f. And so the thing I started out with, the basic fact, so minus the integral from a to b of the modulus of f dx would be less than or equal to integral of f, and that'd be less than or equal to the integral of the absolute value. And now we've got that thing squeezed between a plus and minus bound. We see that this implies that the absolute value of AB, integral AB f, is less than or equal to the thing on the right. This thing is greater or equal to 0. So that's the case. So that's all there is to that. It's the basic inequality. Okay, so now back to the fundamental theorem of calculus. FTC proof. Notice that if I take f of x plus h, that's like a delta x, minus f of x over h, that would be an integral of 1 over h times an integral from a to x plus h, f dt, minus an integral a to x of f dt. And if I draw a picture of that, let's see, the integral from a to, here's a to x. That's this area here. That's that area would be f of x. And then if I take an x plus h, I'd go a little bit further. And when I subtract those two, what I get left with is this little piece of area. So that green stuff there is f of x plus h minus f of x. And so the aha thing, that looks like a big, maybe possibly large thing, but when you calculate it, when you look at it like that, that's just the integral from x to x plus h of f dt. And of course that's a small thing probably, but I'm dividing by a small thing. So that thing better be a really small thing, or equally small thing, I should say. And here's, if you start playing around with this, let's see, there's different ways of doing it. I think I'll do it. I'm going to do it twice. One way is to have played around with this enough to realize f is almost constant on that little interval because it's continuous. So if you think what that means, it's almost f of x on that interval. So let's see if I were to integrate a constant. Let's see. If it was constant, I'll take 1 over h, integral from a to b, not a to b, x to x plus h. I'm going to put a constant here. Namely, why don't I call, to emphasize that my x is a constant, I'm going to change my x to an x naught. There. So x naught is a fixed thing. I'm going to stick a constant, f of x naught, in here, dh. Okay, and so this f of x naught is a constant. And of course, when you integrate a constant over a little interval, that's the height times the width of the interval. That would be equal to 1 over h times f of x naught, the constant, times h, that's the area of that box. And the h's cancel. Okay. And so you think if f is almost constant, we ought to get something that's almost that. And in the limit, we'll get that. That's the plan. So let's see, so I don't have to write this again, I'm going to call this difference quotient, dq. Okay. And now I'm going to calculate, I want to show that thing tends to f of x naught, little f of x naught, as the h tends to 0. Okay, so here's the plan. I want to estimate the difference quotient minus f of x naught. I want to show that goes to 0. I want that to go to 0 as h goes to 0. That would give me the fundamental theorem of calculus. Well, that difference quotient I just showed you is the integral from x naught to x naught plus h, f of t dt. And I just showed you that f of x, well, let's say 1 over h in front of there. And I just showed you that f of x naught is equal to 1 over h integral from x naught to x naught plus h of a constant f of x naught dt. I see something I wrote that's ridiculous. Did I write? Up here, this should have been a dt. That's the area under a rectangle. And I realized, oh, look at now look what I can do. I can stick these things together and get, I'll pull the 1 over h in front, but now I get the integral of something incredibly small. So it's an integral over a small interval of something that's incredibly small, because it's f of t minus f of x naught. That's a small thing, because f is continuous, dt. And now I use that estimate. This is going to be less than or equal to 1 over h times the integral from x naught to x naught plus h times the absolute value of that thing, which is small. And let's see, how small is it? Let's see. Another basic estimate is that this is going to be less than or equal to 1 over h times the max of f of t minus f of x naught on x naught to x naught plus h times the base. And that's where the great thing happens, that those things, the h and 1 over h in front cancels that h. And I'm left with something that I can make go to 0. So that I should have said this is the first sentence, let epsilon be bigger than 0. F is continuous at x naught. So there exists a delta such that f of t minus f of x naught is less than epsilon when t minus x naught is less than delta. And so we get that max there. Let's see, if h is less than delta, I'll make h positive. If h is less than delta, then the difference quotient minus f of x naught is less than epsilon. Check. So sure enough, that thing's differentiable, and its derivative is what you want it to be. Okay, so if I was going to give a freshman picture proof of that thing, what would I do? I got my picture back there. There it is. I would say, oh my gosh, look, when I subtract those things, I get this little tiny thing, and this area right here looks like it would be f of x naught times h, would be the area of the rectangle under the red line. And so when I subtract that off, I'd get the area of that little tiny triangle thing above the red line. And of course that's really small. That looks like 1/2 h times something also small in area. And so I could convince probably my freshman class that that goes to 0, and that proves the fundamental theorem of calculus. But with the careful estimates, it's nailed down for sure. Okay, let's see, another one of my favorite ways to do this, let's see, is to, let's see, I'll say or. I like to do this. I like to write f of t is equal to f of x naught plus an error where e of t goes to 0 as t tends to x naught. That's just what it means to be continuous. Okay, so I can define, this equation defines e of t, and I can define e of x naught equals 0. And that makes it continuous. And so then I would have f of t minus f of x naught is that error that's small. And then I would get, when I do this estimate above, the difference quotient minus, let's see, minus f of x naught would be less than or equal to 1 over h times the integral of this small thing. And then it's I mean, it's exactly the same basic facts, but that makes it clear that you're integrating something small on a small interval. So it's like small squared. And then you divide by something small and you get small. Okay, so that's the first version of the fundamental theorem of calculus. There's a second version. Of the fundamental theorem. And that is, let's suppose f is continuous on AB. And let's suppose capital F is an antiderivative for little f. Suppose f, capital F, is an antiderivative for little f on AB, meaning that its derivative exists and is equal to little f. Capital F prime exists, and it's equal to f prime of x is equal to little f of x for all x in the interval. Then the second version of the fundamental theorem says that you can calculate the area under the graph of little f simply, I'll put dx's here, by subtracting f of b from f of a, capital F of b from capital F of a. And of course that means you can start solving problems in physics by anti-differentiating. It's exciting news. And both Newton and Leibniz figured that out. This follows from the first one in a short order because I'll show you the thing that does it. Questions about anything? Let's see why it follows from the previous one in two seconds. So the why is, let's suppose we have an antiderivative. So let's suppose f prime of x, f prime is equal to little f. Well, the version 1 says we also have version 1 d by dx of this thing is also equal to f. And now ask yourself, if I have two things that have the same derivative, then if their difference would have derivative 0. So d by dx of this capital F of x minus this thing would be identically 0. And the mean value theorem implies that therefore they're constant. That was a corollary. The mean value theorem implies that f of x, the thing inside the square brackets, is identically equal to not 0 but a constant. Okay, and here's how to figure out what that constant is. How to figure out what c is. I can stick in a single point and figure out what c is. Let's see. We know that the integral from a to a of f of t dt, there's no area there under that curve. That's just that's 0. Okay. And so if I stick x equals 0 in that, x equal a in that equation, so let's call this thing star. So plug in x equal a in star, and that would give me f of a minus 0 is the constant. And so the constant is capital F of a. And now, okay, so now I know I would have that f of x minus the integral from a to x of f of t dt is constantly f of a. And now you see it about ready to fall out. Let x equal b now. Then I get exactly what I want. I get the f of b minus the integral from a to b of f of t dt equals f of a. And that's, after I move things to the other side, I get the fundamental theorem of calculus part 2. That's neat. And I think it's the simplest way to demonstrate these things. Questions about that? Okay. Well, now you can do all your freshman calculus is 100% justified. Let's see. Here's an interesting question. Interesting questions. What if we don't know f is continuous? If f is not continuous, but it's Riemann integrable. Think of the Thomé function, that weird thing. Is not continuous, but it is Riemann integrable. Does any of this stuff work? Is there a fundamental theorem? Or does the fundamental theorem make any sense? Or something like it? Let's see. That's one interesting question. When I prove the thing above, let's see. Another question is, if f is Riemann integrable, is its absolute value Riemann integrable? Is absolute f. I needed that. And I got that for continuous functions. It's a no-brainer because the absolute value of f is continuous, if f is continuous. But my proof that I gave of that I'd have to think about it in this case. So that's another thing to think about. Okay, so the first thing to observe that some of that proof I did goes through. So let's see, here's some steps toward these things. If f is Riemann integrable, then that thing, the capital F of x, which would be the integral from a to x of f of t dt, is continuous. That's nice to know. I'd like it to be differentiable. Okay, let's see. Why would that be true? That's an easy thing to see. If I take f of x minus f of x naught, when I write that out, I'd get an integral. Let's pretend x naught is bigger than x. And we know that if f is Riemann integrable, it has to be bounded. And so this would be less than or equal to the max, or the sup, of the f, let's see, on the whole interval times x minus x naught. So in this case, I'm taking x bigger than x naught. And so we get a Lipschitz estimate. So in fact, f is Lipschitz continuous. So this would be this is equal to m, which is finite. And therefore, in fact, f is Lipschitz continuous. So that's nice to know. And then that means that I can do exactly what I did above. At least at the spots where little f is continuous. So the argument above shows f prime of x equals little f of x at points x where f is continuous. Okay, so that's a fact. And here's a fascinating example, the Thomé function. Remember what that is? F of x equals 0 if x is irrational, and it's equal to 1 over n if x equals m over n is rational. And to make that n unique, you factor this out and make them have no common factors. So they're relatively prime. That's the Thomé function. And the famous thing we showed is it's continuous at all the irrational functions. It's continuous at irrationals. And it's not continuous at rationals. And here's a fascinating function, almost as interesting as the Thomé function. Let's define the capital F of x to be the integral of the Thomé function. Integral from a to x, where this is the Thomé function. Then f prime is differentiable on the irrationals. Let's say then we know that f is continuous. I just showed you that. And f prime exists at the irrationals and is equal to 0. I guess this is not an interesting function because this function is identically 0. F is continuous, it's f prime exists at the irrationals and is equal to 0. And f prime doesn't exist at the rationals. Let's see. see, in fact, I should say, f is identically 0. Wait a minute. Yeah. Yeah. Let's see. Let's see, what else do I want to do today? I've got 10 minutes. I guess I would tell you what that famous theorem I told you from last time, it's called Lebesgue's theorem. If suppose we have f is bounded, so number 1, f is bounded on AB, and 2, f is Riemann integrable. That's sorry. So f is Riemann integrable is equivalent to, number 1, f is bounded, on AB, and 2, it's continuous almost everywhere. Which means everywhere but on a set of measure 0. So of course the Thomae's function is Riemann integrable. The book uses this to prove as a corollary if f is Riemann integrable, then so is the absolute value of f. It's kind of a sneaky trick. Let's see, why is that true? If f is Riemann integrable, that means it's bounded and continuous almost everywhere. And wherever f is continuous, the absolute value of f is continuous. So it just falls right out. So here's why. Absolute f is continuous wherever little f is. And so if f is on a continuous almost everywhere, then so is modulus of absolute value of f. So f continuous almost everywhere would imply that absolute f is 2. And so Lebesgue's theorem would say the absolute value of f is integrable. Cheating. It makes absolutely no work. That feels like enough for today. I have Eclipse psychosis also. I'm running out of steam. Okay, this is a pretty important chapter because, or section, because it's going to do the Taylor's theorem with remainder, but it's going to be the integral formula for the remainder, which is a very important tool. Anyway, I'll let you read that before I talk about it next time. Okay. Enjoy your afternoon.